Hello, my wonderful Gen Chem students. Let's switch to a new topic, which is called common ions, buffers, and then eventually titrations. This is actually the lecture that I was coughing so hard and I completely blundered it. So hopefully this makes a lot more sense and you can hear me without all the coughing. All right. So, what kind of equilibria is going to happen when we have combinations? Okay, so we just saw in the previous chapter what will the cation and the anions have on the water? Will it turn acidic, basic, neutral? Okay, so in here, we're actually going to do some combinations. So we're going to start with something called the common ion effect. Okay, so basically think of this as Le Chatelier's principle. And granted, everything we've been doing could be considered Le Chatelier's principle. But when you think common ion, literally think Le Chatelier's principle. All right, so we're going to just use vinegar as an example. All right, before when I was doing Le Chatelier, I said, hey, what if I increased the amount of acetic acid? Okay, so I'm at equilibrium. Okay, better make note. Oops. I'm at equilibrium, but I'm adding some extra acetic acid. Well, the reaction now has too much acetic acid, and so it needs to shift to the right, and therefore it's going to create more of the protons and more of the acetates. Well, what if I was to put in some extra acid? Okay, so I'm at equilibrium and I'm going to pour some acid, maybe some hydrochloric acid or some hydrobromic. Okay, somehow I'm going to put more protons in there. Well, the shift is going to go to the left to the weak acid side. And this one would also shift it to the left. Okay, so just generic, Le Chatelier's, but we want to look at their identities now. So, did the thing you add, okay, what you added, is it already part of the equation? If that answer is yes, then you're just dealing with a common ion. But there are different types of common ions. This one has a very special relationship. So in this reaction, if you added extra acetate, okay, so this is the weak acid base pair combination, that would be called a buffer. If you just threw some extra protons in there, red, if you just added some extra protons, well, that would just be called a common ion. All buffers are common ions, but all common ions are not buffers, okay? And we'll play with that, of course, a lot. Here's our combinations for the titrations. Well, what happens if you combine strong acids and strong bases, weak acids, weak bases, and strong acids with weak bases? Okay, so the buffer is the one that we just saw. That's the weak acid conjugate base pair. What if you do a strong and a strong, a weak and a strong and a weak? Notice I do not have a weak combination here. We could figure that out. It would just take more calculations, and we're not going to go into that depth for this class. These are called titrations. So now that is what's going to happen every time we do a combination of things. All right, what are my choices so far? I could have, let's see, a weak acid. I could just have a weak base. If I just added water to it, that's just diluting. Ah, I could have a buffer, which would mean I added the weak acid conjugate base pair. I could have a common ion, which means I added an ion other than a buffer. I could have added a strong acid with a strong acid. I could have added a strong acid with a weak base. And I could have added a, let me see, who didn't I do? Strong acid, weak base, a strong base with a weak acid. And technically those are titrations. Those are all the combinations that we have now seen. This was basically last chapter. This one is just changing the numbers because you're just diluting things. And let's try the buffers. All right, what in the world is a buffer and what is its purpose? Okay, it is a weak acid and its conjugate base pair, or a weak base with its conjugate acid. All right, you can have either. You can have either. It's just the weak conjugate pair. We tend to usually just say weak acid and its conjugate base. Its purpose is it is highly resistant to changes in pH. And when I say highly resistant, I mean really highly resistant. And its pH is approximately the same as its pKa. All right, the pH is not the pKa. Okay, those two identities are completely different. But if you're in a buffered situation, it just so happens that the pH is approximately same as the pKa. Well, why is that? Well, let's just do our equilibrium expression. So here's my weak acid, and I'm ionizing it into the proton and the conjugate base. And so there's my Ka. Beautiful. Equilibrium is established without changing the initial concentrations. What? What? So here's the difference. You are starting with an initial amount of one of the products. So for instance, in my little ice table, let's say I started with 0.1 molar here. Well, guess what? If I have 0.1 molar here, but I didn't add any of those in, okay, if those are my initials, do you see it's going to basically cancel each other out because the weak acid is trying to shift to the right, that weak base is trying to shift to the left, and in this case, they're equal, and so you're not going to change the initial concentration of that weak acid at all because Le Chatelier has shifted, or if you will, reestablished it so that it has done absolutely nothing. Don't forget, if you add two together, you must consider dilutions. All right, so let's kind of play with that. So the acid and the conjugate base are present in the same solution. So their concentration ratio is the same as the mole ratio. So when I write the brackets of HA over the brackets of A minus, really what I'm saying is the moles of the weak acid over the total volume is divided by the moles of the conjugate base in the total volume. Guess what cancels out? The two volumes. So basically it's the same as just the mole fraction. Of the weak acid conjugate base pair because the volumes are always going to be the same. So if you combine them together, their volume, their total volume is always going to be identical. So if you divide one thing by another, that part's just going to go away. And so basically I have the mole fraction. And again, Jolly, yeah, you're talking, but you're not getting through here. Okay, don't tune me out. Don't tune me out. This is going to lead me to something very special called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch can only be used if you have a buffered solution. Because of this identity where those total volumes cancel out. So I'm going to take the negative log of this. Let's see, so the proton times the moles of the acid over the moles of the conjugate base. Okay, bear with me, I'm just trying to put a visual in there. And I'll take the negative log of both sides. Remember, all that does is change the values into a more manageable number. But if you whip that thing into a beautiful form, the pH is the same as the pKa plus the log. Here's the nice piece of the A minus over the HA. Yes, I know that's backwards than the original, but remember I took the negative log of this. And what do I know? That can also be written as the moles of the A minus over the moles of the HA. That is the power of the Henderson-Hasselbalch. Let me peek at our next one. Oh, that will be the next lecture. I'm going to run over to the whiteboard here. Yeah, run, as if I'm running anywhere. Okay, so let's take a look now at that all combined together. So I have, let's see, let's just use acetic acid. Just like we've always done in the past. All right, so here's the question. I'm going to combine 10 milliliters of 0.10 molar acetic acid. Okay, now if I only had that, that would just be a weak acid problem. But I'm going to combine it with, let's go 10 mils of acetate. Now, it could be sodium acetate, lithium acetate, okay, as long as it's one of the 100% soluble ones. What is my new pH? The first step has not changed. You have to have an equilibrium equation. And in this case, they're part of the same equation. So the acetate and the acetic acid are both part of the same equation. Oh, look, I know that one. It's this. Okay, do you know your initial concentrations? I cannot plug 0.1 moles in here because M1V1 is equal to M2V2. So if I have 0.10 molar 10 mils, I'm going to end up with M2 at 20 mils. And in this case, M2 will be half of that. Okay, because my initial concentration here, when I'm starting equilibrium, means the concentration at that moment, not necessarily what you put in. So I'm actually going to plug in 0.050. And how many sig figs do I get? Just the 2. I didn't start with any protons, but again, I had 10 mils of the acetate and 10 mils of the acetic, so this one also gets diluted. Oh, okay. The change has not changed from all of our other equations. And so at equilibrium, we're going to have 0.050 minus x. We're going to have x, and we're going to have 0.050 plus x. Here's the difference. Here's the difference. You have a reactant and a product. You have both of those in there. And what is their relationship? In this case, yes, it's a common ion because it's already part of the equation, but it's the special common ion called a buffer. It's a special one called a buffer. Now I'm going to do the long way, and then I'm going to show you where the Henderson-Hasselbalch comes into play. Oh, hey, that's no big deal. I can still do this. 1.8 times 10 to the minus fifth is equal to x times 0.05. And this one is a plus x on top. And it's 0.050 minus x on the bottom. Is this a weak acid combination? The answer is yes. So I may ignore that because the same amount being formed is the same amount being lost. And guess what happens? These two concentrations actually, in this case, because they're equal, it goes away. And so x is equal to 1.8 times 10 to the minus fifth. Well, what is x? X is, in this case, your proton concentration. So if you take the negative log of it, the pH is the same as the pKa when the moles are equal. When you have the same number of moles of the weak acid and the conjugate base, they just divide out in your equilibrium expression, and your pH literally becomes your pKa. Okay, well, that didn't seem so hard, but if I recognize this, I could have just started with a shortcut, and that is the Henderson-Hasselbalch. If I recognize it as a base, I could have said, oh, look, if I want the pH, okay, the pKa of acetic acid is 4.74. We can get that off of the reference sheet, plus the log of the 0.050 divided by 0.050. And because they're the same, the pH is the same as the pKa because this becomes the log of 1, and that goes away as 0, and that goes away as 0. That's where the Henderson-Hasselbalch comes into being. But you have to recognize that it is a buffered solution, not just a generic common ion solution. It has to be a buffered solution. And if the buffer, if both pieces, the acid piece and the base piece, have the exact same number of moles, which means they have the same number of molarities, okay, then the pH is the same as the pKa. All right, I'm just going to erase this whole thing again. We're going to do vinegar again. So this time I'm going to put in 10 mils of the HAC and 20 mils of the acetate. Okay, sodium acetate, there's always a counter ion. And let's start with 0.15 molar acetic acid. And let's start with, just 0.100 molar acetate. Okay, and so remember, ions don't exist by themselves. You would have added sodium acetate, but I would have ignored the sodium. So basically, I'm just adding acetate. All right, so what is the pH when you combine 10 mils of a 0.15 molar acetic acid solution and a 20 mil 0.1 molar acetate solution? All right, step number one, if you're combining two things together, the concentrations have to be diluted. All right, well, let's just do that before I even start my problem then. So HAC would be 10 mils times 0.150 is equal to, let me see, 20 plus 10, which is 30 mils, with my new molarity. So I'm going to divide both sides by 30 mils. That part goes away. Milliliters are gone, and my answer is going to end up in molarity. And so my final concentration, so M2 or final concentration, is going to be 10.15 and 30. Oh, wow. Look at that. I didn't mean for it to come out to 0.050 again, but it did. All right. Well, that's what my acetic acid solution is going to do. Let's ask what the acetate will be doing. Hey, acetate, what's your new concentration? And this time I had 20 mils of a 0.10 molar solution, and there's 30 mils of the total solution, M2. So I'm going to divide both sides by 30 milliliters. My milliliters are gone. In this case, remember, you can plug in milliliters because they will cancel out. If you plug in a milliliter, you'll divide by a milliliter. All right, so 20 times 0.1 divided by 30 is 0.067. Double check. 20 times 0.1, 30. Yep. Okay, now let's plug them in. As the initial concentrations. All right, so 0.050 and 0.067. Okay, so that's what I added. I didn't add any protons. And the Ka is equal to, there is nothing wrong with solving this the way that we have always done. It's a lot longer if you don't recognize it as a buffer, but there's nothing wrong with plugging and chugging right now as it is. Because I could do my assumption and off I go. Okay, yes, that can still be done. But what I want to recognize is that combination is a buffer. If I recognize that combination as a buffer, then I can use the Henderson Hasselbalch. You're probably thinking, well, I don't see how that's going to speed things up. If you recognize it as that, you can do a lot of calculations very quickly without having to reset up the whole ice table. Ah, here is my fun new trick for you. If you are buffered, whoa, she's writing that in capital letters. If you are buffered, you can plug moles into the table instead of constantly going out and figuring out the new dilution. Because what do we know about buffers? The volumes will always be the same. So really, I'm only interested in the mole fraction. Okay, don't really care about the overall molarity because their volumes are the same. So you may plug in moles instead of concentration. Oh, well, let's make sure we're going to get the exact same answer. So, wow, Jolly, you write so big. All right, let's get rid of that. let's just calculate this and see what we get. All right, so the long way, or I should say the old way, is 1.8 times 10 to the minus fifth is equal to the proton times 0.067 plus x all over 0.050 molar minus x. All right, I'm going to do my assumption. And so my proton concentration is going to be 1.8 times 10 to the minus fifth times 0.05 and divide both sides by 0.067. My new proton concentration is going to be 1.8 to the negative fifth, 0.05, 0.067. And that is 1.3 times 10 to the minus fifth. All right. I just found the proton concentration at equilibrium if I took the negative log of it. That is 4.87. 4.87. Okay, well, let's try this the short way. So now I can erase this bottom part. All right, rid of that part too. All right, so the pH is 4.87. All right, so I'm going to start the whole problem over again. Hey, look, I combined acetic acid and the acetate, so my equation is this. But I am starting with some of that, and I'm starting with some of that, so I'm going to go straight to moles. I'm going to go straight to moles, and I write myself a little note here that I'm in moles. And so what is 10 milliliters of acetic acid solution? If you want to use molarity, if you're going to do the calculation, not the dilution, you do have to be in liters. So 1,000 milliliters in 1 liter, and I know for every 1 liter there is 0.150 moles. So in that 10 milliliters, I have, whoops, that calculation didn't work. I have two zeros, 0.00150 moles. Okay, I didn't start with any proton moles. And acetate, 20 milliliters of my sodium acetate, convert to liters. And for every 1 liter, there is 0.10. So 20 mils divided by 1,000 times 0.1, 0.002. All right, now that seemed like a lot of work right now, but I promise in the future it's going to save us time. Oh, okay. Now I have, come on. How about I just keep drawing lines all over the page? Now I can finish my ice table. So minus x, 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 and 0.00150 and 0.00200. And I can plug that in, and I'm going to get the exact same answer. So 1.8 times 10 to the minus fifth is equal to x times 0.00200 plus x, 0.00150 minus x, make my assumption, and my x is going to turn out, let's just double check, so 1.8 to the negative fifth times 0.0015 divided by 0.002. Look at that, 1.3, and depends on how you round, 1.3 or 1.4 times 10 to the minus fifth. Oh, look, they match, because in a buffered situation, I'm really only concerned with the moles, not necessarily the molarity. And if you take the negative log of that, it's within rounding at 4.87. Okay. Really, Jolly, it looks like you're just making work for yourself. I promise it will help in the future. I could have just recognized, oh, look, this is a buffered situation. I could have just used the Henderson Hasselbalch. So the pH is equal to 4.74 plus the log of the base piece over the acid piece. So now I could change these number of moles, and I have this wonderful starting equation. So the pH is equal to 4.74 plus the log of my base piece over my acid piece. And guess what? You will get the exact same answer. All right, we have not played with it a lot, but let's do a little highlight. In this chapter, we're going to talk about buffers. We're going to talk about titrations, but this little section, let's just focus on the buffers. All right, what is a buffer? It is a weak conjugate acid base pair or weak base conjugate acid, or anyway, the conjugate acid pair, the weak acid conjugate base or the weak base conjugate acid, and it's going to resist changes to pH, and we can plug in moles. Okay, that's my most exciting part so far. We can plug moles into the Henderson-Hasselbalch, and the Henderson-Hasselbalch is just the equilibrium expression manipulated. Okay, can you, given those two numbers, just come up with the pH? And you're going to be doing that a lot. So until next time, jolly out.